25, Mark. Okay, so I think, Mark, we might as well get started. Maybe if you could keep an eye on the people signing on as well. We're still missing one speaker, or that's for the last talk, so hopefully they'll get on later. So welcome everyone to this session. I'm Paul McCarr from Environment Climate Change Canada, and our co-host is Mark Gordon from York University. And I think in the interest of time, we'll just start in. I will be announcing the speakers. Mark will be timing you, and he'll give you a 15-minute warning. So you know we also have sort of a 10-minute health break in the middle of this session, and we could potentially set for additional questions as well. So with that, I think, let me just share my screen. I'm the first one up. This is a special session on oil sands work that's going on right now, air pollution and air quality work. So I've got an overview here that talks a little bit about some of the work we're doing in Environment Climate Change Canada. So I'll launch into this, and Mark, keep me honest. Give me the 12 minutes, give me the warning, please. We have 3 minutes left. Okay, thank you. And let's go ahead. So, yeah, so we get talking about GEM-MACH simulations and doing an overview of that. For those who are unfamiliar with Environment Canada's air quality model, this is the Global Environmental Multiscale Modeling Air Quality and Chemistry Model. And we've been a partner in the Oil Sands Monitoring Initiative in collaboration with Alberta Environment Parks and First Nations and Industry since 2012. And ECCC's air contribution included 3 major air pollution field intensive campaigns involving aircraft and surface observations. And we continue to contribute to the oil sands monitoring work through working up the above data, ongoing surface monitoring, and air quality modeling. And so that's what I'll be talking about here. And there'll be several other talks in this session that relate to the GEM-MACH work as well. And let's see if I can get my page down to work. There we go. Okay. So first of all, what is GEM-MACH? It's a comprehensive online, fully coupled nested regional air quality model. I've sort of described what I mean by that. We try to include all of the processes for all chemical and physical processes, including reactive chemistry of the pollutants. It's online. It runs as a subroutine package within the weather forecast model. It's the fastest way to do chemistry in a massively parallel computer, especially if you're doing high resolution nesting. It's fully coupled. It includes direct and indirect feedbacks, and it's nested from a 10-kilometer North American domain, which I'm showing on the outside here, to a 2.5-kilometer resolution Alberta Saskatchewan domain. And if I blow that up, you can see this is just a snapshot of PM 2.5. But you can see sort of the high areas right here for PM 2.5. That's from oil sands anthropogenic PM plumes, both primary and secondary combined. Take a look at that in a little bit more detail. That's the local monitoring network that the Wood Buffalo Environmental Association runs right in the oil sands area. There's other monitors that are part of national networks over a larger region, especially to the south. We've done evaluations with both of them for our model runs. So not to go into these in too much detail, sorry, the top part showing up there. Let me go back. The speciation that we're using and the particle speciation and a lot of other things have been added into this recent version of the model. Some of these, we've already had a few talks in other sessions of them, Saprophytes plume rise, for example, Saprophytes, sorry, and the Stefan's work is going to be later on today. Roya's work was shown a couple of days ago. Collins will appear in this meeting. Deborah's will appear in this meeting as well. And Jack's already presented this as well. Bottom line, there's a lot of new stuff in this model version. We've done 2 simulations for the period August 1st, 2017 to October 31st, 2018. So that's 15 months. And we were evaluating it using 2 different data sources. The larger monitoring networks, and that's for the entire 2.5-kilometer domain. And then the Wood Buffalo Environmental Association data, and that's within 320 kilometers of oil sands operations. And there's the second run is within a couple of days of finishing. The first run is what we'll be talking about here in the initial evaluation of it. So this is an example of the kind of thing that we're doing. This is for NO2. Now on the left, I've got the larger monitoring network. These are scatter plots for the whole region. And the shading in these shows the number of model measurement pairs falling within a given cell. So the darker it is, the more pairs at a given location. So you can get a feeling for where most of the model measurement pairs are showing up. So it's model on the the y-axis, observations on the x-axis, and number of pairs that's been shown there. If you blow up those things, you can actually read them. That's our correlation coefficients, normalized mean bias, root mean square, and number of points that are within a factor of 2 for each of those months. And you can see that there's a negative bias that's happening in the wintertime that goes to almost nothing in the summertime in the larger area. These images on the right are for the Wood Buffalo Environmental Association area, and the numbers there are the values at the stations. This is a Krieg plot, and it's using extrapolation outside of the measurement area. So you can't really necessarily trust anything that you see in either of these. It's really within the dots that you need to focus. But the key thing is that we get the same sort of pattern from the observations and the model, and relatively similar concentrations too. This is for the whole period. So within that region, the shape and magnitude of NO2 matches pretty well. Over the entire domain, however, we can see we have a low bias in the colder months. For ozone, we saw something interesting there in that we had a similar pattern of ozone titration close to the sources of emissions. That's these shaded areas here. But there are two different color scales being used. The values for the model are overall much lower, about 8 parts per billion or so. And you can see that especially in July, we're biased low, but also especially in April as well. And there's our normalized mean biases and correlations once again. And you can see it generally it's a negative correlation, and it's the biggest negative correlation in the springtime. So we see titration, and over the entire domain, you see a low bias in the springtime. When we took a look at that in a little bit more detail at one of those measurement sites close to the oceans, we can see that the bias is really strong in the early spring. That is, the model is biased low. It does get a little bit of the shape there happening, but it doesn't get the big springtime peak. That's a time series that comes from Kevin Strawbridge's ozone LiDAR that's at Fort McKay, and it's just looking at the number of stratosphere troposphere fold events within the same time period shown on the left. And you see how nicely it seems to match up. It matches up to the point of a correlation coefficient of about 0.86 with the ozone at the passive site. So it really suggests that it's probably troposphere stratosphere exchange. For PM 2.5, here's the plots we have for that. These gaps are because the monitoring network that's being used here is only reporting in intervals of 1 microgram per meter cubed. So there's gaps in the measurement record as a result. And overall, what we get from this one is that PM 2.5 is biased high in the colder months, low in summer. And then from the local monitoring network, within the interpolation region, PM 2.5 is biased high in the model close to the mining, the open pit surface mining area, and it's biased low outside of that. For SO2, the spatial pattern is pretty good. We don't have that for the larger monitoring network, but we have a low bias. And this one is almost certainly due to emissions. There's a couple of papers, one by Chris McClendon, who'll be presenting the last talk in the session, that show that based on satellite observations, the reported emissions are probably low for SO2, and this is almost for sure influencing the model low bias in this case. We're working on that for the second 15-month simulation. That's an example from Chris's paper in 2020, with that's the reported SO2 as a function of year. This is what was estimated from service monitoring networks and in particular satellite data. Surface monitoring networks match up with these points, which are satellite estimates from OMI. For ammonia, it was interesting there in that the stations right in the center are biased low in the model. And what we seem to be seeing from that is that there's emissions that are missing. So there's emissions that are missing again in the inventory for ammonia relative to what the model has. So all of these things are pointing us to things that we can focus on for improving the model performance. There's HNO3. Now for the first model run, HNO3 was biased quite high. And what we've seen so far in the second model run is that Stephen Miller's particle chemistry, which we'll be talking about later in the session, seems to be correcting a good part of that. So I'm quite excited about that. We'll be seeing later what that does. So summary, what we've learned so far, this is very much a work in progress, but for NO2, we've got a low bias. It's very dependent on the rate of NO2 losses on particle surfaces, as it turns out. We've got chemistry in there for that. And these have several orders of magnitude variation in literature. So we think that probably a good thing to do would be a sensitivity run with different surface loss reaction rates. For NO2 conversion to HNO3. In a couple of slides, I'll get to that, but that's one where the surface chemistry, excuse me, the inorganic heterogeneous chemistry seems to be controlling the HNO3 concentration. We saw tropopause fold events showing up in Kevin's LiDAR, and there seems to correlate very well with our negative bias. We have a published methodology we can use in GEM-MACH to try to include those sort of things, at least as the boundary conditions, and we think that'll improve results. We'll try that next. We've seen things like the positive bias in PM 2.5 and colder seasons, and as it turns out, one of the things that we think is a big contribution to this is the primary PM size distribution, which we're working on right now. We base it on the local observations. We had it based on aircraft observations. Surface observations seem to suggest it's more in the close mode, so we're going to make use of that. We have summer negative bias in PM 2.5. There's surface conversion of NO2 to HNO3 that's dominating that, and we think that Stephanie's new particle chemistry is going to fix it to a large degree. There's a negative bias in stations to the south and one to the north of Fort McMurray, and we're taking a look at the primary PM emissions, especially for the in-situ facilities, to try to address that. The SO2 is biased low, but that's something where it's a known problem with the emissions. And our second 15-month run is using revised emissions and a revised plume rise algorithm that SEPR-FAFI has done. And that we think that'll improve the SO2. Ammonia, we need to do some sensitivity runs on the ammonia emissions near the sources. And HNO3, once again, that's likely inorganic heterogeneous chemistry. And Stephanie will be talking about that later in this session. So that's a very quick run through of some of the work that we've been doing with GEM-MACH, comparing these simulations in the oil sands to observations both over the larger region and close to the oil sands themselves, within about 220 kilometers. So just want to acknowledge that we've also been receiving a great deal of assistance from the Wood Buffalo Environmental Association, and financial support for this work is from the Oil Sands Monitoring Program. And that's it. So Mark, where are we?
Thanks, Paul. You got a few minutes for questions. Good timing.
Okay. So any questions, please?
Seeing Youngshin.
Yeah, go ahead.
Hi, Mark. That's a very good talk. I really enjoyed. So some question about the bias. You showed that the bias vary with season. How does it relate to meteorological field?
Sure.
Bias?
One of them, it depends on the chemical. But for example, this one, we're not. I didn't show the some of the LiDAR profiles, but you can actually see the ozone coming down from above, and it looks like it gets caught up in convective systems. It doesn't get all the way to the ground from the fold event, but then the convection is what gets it down. So we need to improve our ozone transport that gets it to the middle to lower troposphere. And I think after that, because we're running a 2.5 kilometer and we've got cloud resolving scale at that point, we should be able to get it down. So that's one meteorological thing. Others, let me just think here. Things like the PM 2.5, part of what's happening with this one, there's temperature issues too with this. They're very temperature dependent reactions. We haven't checked out the temperature biases yet in this model version. We sometimes, in the past, there was a tendency, at least about 2 or 3 years ago in the region, for our temperatures to be biased maybe a couple of degrees low, which doesn't sound like a lot. But some of the temperature, the reactions for particle formation, for particle nitrate, are so temperature dependent that it could have an influence here, but we just have to see for that. I'm thinking other things related to the meteorology. The SO2 is another one that's dominated by large point sources, the big stacks in the area, and those are the chemical distribution. The vertical is dependent on the temperature profile. So how well we do the temperature profile is part of the issue. And SEPR's work has focused on trying to improve the algorithm for that. I think he's got something where for the first time ever, we're including the water that's released from the stack sources and latent heat release from that as it condenses. And it's actually improving the results a fair bit. But that's one where the meteorology is interacting again with the chemistry. I mean, I can rattle off all the possible things. Does that answer your question? I mean, that's some of the meteorological connections.
Yes, that's good. Thanks.
Oh, and one other too is, we're running this, as I mentioned at the start, in feedback mode. So all the particles in these simulations are creating clouds. They're creating, or they're also affecting the radiative transfer, the direct effect. So when we change the emissions, when we change, anything in there, we're actually changing the weather as well. So that is, you can see that happening in the results when we focus on the cloud field. Any other questions?
I think that pretty much takes us.
Oh, sorry. Okay.
We were sort of on time, unless there's a really, really fast one.
No, that's good. Let's keep it on time, and
Yeah,
we can always return later. So,
okay.
so I'm going to continue on then with just introducing people. Our next speaker is Jan Hu, and she'll be talking about contributions of emissions from the oil sands activities to atmospheric concentration and deposition of nitrogen and sulfur at a downwind site. Go ahead, please share your screen and make sure that you're not on mute, which you are at the moment.
Hello, can you hear me clearly?
Yes, we're good. Yep.
Yes. Hello, I am Yuan Yu. I'm going to show you a result of my recent analysis on contribution of emissions from the oil sands activities to atmospheric concentration and deposition of nitrogen and sulfur species at a downwind site. And I lead the analysis, and this research is a group effort from my supervisor, my colleagues in Air Quality Research Division, and we acknowledge the financial support of the oil sands monitoring program. We also thank the CAPMON program and the data team. As Paul already provided an introduction about oil sands region, the facilities and operations in the oil sands region are large sources of NOx and SO2 emissions. Most previous studies on nitrogen and sulfur deposition focused on regions within about 50 kilometers from the center of the oil sands facilities. And this study investigated the atmospheric concentration and deposition of nitrogen and sulfur species at about 350 kilometers downwind of the Athabasca oil sands facilities to understand the long-range impact of NOx and SO2 emissions. In the next few slides, I will show you a map of the site and the oil sands region. Data and the measurement used in this analysis study is from a Canadian Air and Precipitation Monitoring Network, CAPMON. The study period is from 2015 to 2019. Data used include air filter pack concentration, 24-hour integrated for nitric acid, SO2, sulfate nitrate ammonia in particle phase, and base cation and chlorine. And precipitation data include precipitation depths and the daily concentration of sulfate nitrate ammonia, base cation and chlorine. The site also includes ambient continuous concentration. In this study, we used the 5-minute average concentration of NOx, NO, NO2, ammonia, and SO2. Dry deposition in this study is calculated using the inferential method. Dry deposition equals the dry deposition velocity times the ambient air concentration. And dry deposition velocity is calculated using the previous algorithm for gases and fine and coarse mode particles. Wet deposition is straightforward. The daily wet deposition is calculated as the daily precipitation concentration times the precipitation depth for nitric, sulfate, ammonia, base cation, and chlorine. This map shows the site used in this study in Panhouse Lake site, located in the boreal forest of Saskatchewan, and it is 350 kilometers away from the Athabasca oil sands region, circled in red. And to study the air mass, or four sectors are defined in this study to investigate the contribution of oil sands. The oil sands sector covers the oil sands region. The clean sector has minimum anthropogenic sources and is used to estimate the background concentration and deposition. The southwest sector have Edmonton, Elk, and Calgary having some urban point sources of NOx and SO2. The Saskatchewan sector studied here also has some NOx and SO2 point sources. And the southwest sector and Saskatchewan sector are investigated in this study for the bulk comparison to the oil sand sector. And these two sectors are not used for any particular individual point sources in them. High split air mass trajectories are used to understand the air mass origin of the sulfur and the nitrogen species measured at this site and used for sector analysis. For dry deposition, trajectories start at half of the boundary layer height, starting at every hour, every day. And for wet deposition, trajectories start at 1 kilometer above ground level, starting at every 3 hours for days with precipitations. And to conduct sector analysis, the first step is to assign each trajectory to one of the 4 sectors. Second, to assign each day to one of the 4 sectors. For trajectories and days which don't meet the criteria are assigned as the not assigned group. And 35 days are analyzed separately as the fire influenced days to minimize the influence of wildfire emissions to the later on contribution calculation. And here are examples of sector assignment. These 2 panels shows 2 example days got assigned to oil sand sector, and this panel shows a day assigned to the clean sector, and this shows a day assigned to the Saskatchewan sector, and this one assigned to Southwest sector. These 2 are examples of days don't meet the criteria and got assigned to the not assigned group. So here are results. On the y-axis of each panel shows the ambient air concentration of this species, and on the x-axis are for the daily concentration for the 4 defined sector plus the fire sector and the not assigned group. For nitric acid, particulate nitrate, particulate ammonia, NO2, SO2, particulate sulfate, the medium concentrations in the oil sand sector are significantly greater than those in the clean sector. And this is in the expectation since NOx, the main sources of NOx and SO2 emissions in the oil sand region are the stacks. Compared to the particulate sulfate, it is interesting to see that the significant difference of the SO2 concentration between the oil sand and the clean sectors suggests a significant amount of emitted SO2 could transport downwind before being oxidized to sulfate. And here are results with the exact same layout as the previous slide. This time on the Y are the daily dry deposition of the same species. And you can also see that the medium daily dry deposition in the oil sand sector are significantly greater than those in the clean sector. And the relative difference of the medium dry deposition between the oil sand sector and the clean sector are very close to the relative difference in medium concentrations. Here are the results of precipitation samples. On the first row shows the precipitation weighted mean concentration of nitrate, sulfate, ammonia, and the precipitation weighted mean concentration in the oil sand region is significantly greater than those in the clean sector. And then on the second row shows the daily wet deposition of nitrate, sulfate, and ammonia. And again, the daily wet deposition in the oil sand sector is significantly greater than those in the clean sector. The goal is to calculate the contribution of oil sand emissions. So on the pie on the left shows, so this slide uses the nitric acid dry deposition as an example to show the method of calculation of contribution. The pie on the left shows the total dry deposition of nitric acid in each of the sectors contributing to the total dry deposition of nitric acid at the site. And this colored slide shows the contribution from each defined sector. As you can see that the not assigned portion is significant here, since the not assigned portion contains a significant number of days. Therefore, another steps is needed to partition the 4 defined sector contribution in the not assigned group. So in the second step, the fractions of endpoints of trajectories during those not assigned days in each sector, and the relative concentration of each sector to the not assigned sector are considered. And then the result contribution in the not assigned group from the 4 defined sectors is presented in the lighter color slices in this pie. So for the oil sand sector contribution is the total of the dark red and light red slice. After getting the oil sand sector contribution, we wanted to get the anthropogenic contribution from the oil sand sector. So the excess flux is considered and calculated as the relative difference between the oil sand concentration and the clean concentration. So the contribution of the oil sand emissions in the oil sand sector is calculated as the contribution from the oil sand sector times the excess flux. So each species wet or dry deposition in this study is calculated in the same way to get the contribution from the oil sand emission, and the result is summarized here. Dry deposition and wet deposition of this species. The first column shows the contribution of the oil sand sector, the excess flux, and the contribution of the oil sand emissions. And as you can see that the oil sand emissions contributed the most to the dry deposition of SO2, followed by the NO2 and nitric acid, consistent with the expectation since SO2 and NO2 are the most abundant primary pollutant in the fresh plume from the oil sand region. And oil sand emissions contributed to about 13%, 9%, and 9% of the wet deposition of nitric, sulfate, and ammonium. Another point not shown in this table is wet deposition dominated the total deposition of nitric and sulfate at this site. So here, and then merge the dry deposition and the wet deposition. Here are the result of the contribution of each sector contributed to the total deposition of oxidized nitrogen, reduced nitrogen, and sulfur species. And then the red color shows the oil sand contribution, and this oil sand sector contribution, and this color shows sectors from other sectors. And after considering the excess flux in the oil sand sector, the contribution of the oil sand emissions are about 12%, 8%, and 11%. And here are the summary. So for the medium ambient concentration of the measured species in the oil sand sector are significantly greater than those in the clean sector. This is also the case for the medium daily dry deposition, and precipitation weighted mean concentration of the nitric, sulfate, ammonia in the oil sand sector are also significantly greater than those in the clean sector. And the wet deposition dominated the total deposition of the nitrogen and the sulfur at this site. And in the end, the contribution of the oil sand emissions to a total deposition of nitrogen and the sulfur species are quantified. And thank you for your attention. And I'm open for questions.
Okay, thank you. And then Juan, are there any questions?
Hi, Yuan.
Yes.
It's very interesting to me that Saskatchewan seems to be a pretty heavy contributor to almost everything. Do you think that maybe has to do with the proximity and size of the sector, or like why does Saskatchewan seem to be such a big contributor to a lot of these species? I just found that very interesting.
Yes. So first, yes, as you can see that the Saskatchewan sector is a bit wider, and then that will include more number of days. And a second reason is that according to the MPRI, there are a few point sources of NOx and SO2 down here, and even here extended to Manitoba, and then they can also be significant contributors in this sector.
Interesting. Okay, thank you.
You're welcome.
I have a question too,
Yes.
Dawn. What do you think the possibility might be? Like for the way the sectors are defined, for example, if emissions from the oil sands went north and then curved around, so they came from the northern section, or if they went south and curved around, so they came from the southwest section, you know, is there potential that they could be potentially counted as part of the other sources or not?
Yes.
You know what I mean?
Yes. So I didn't have enough time to introduce the details, but first, so basically so for each trajectories, I try to have a threshold, and then that means the trajectory has to have a dominant fraction of time in one of the 4 sectors to get assigned to the sector, for example, oil sand. And then the second step is that each day for dry deposition has 24 trajectories, for wet has 8 trajectories. And then they must have a dominant number of trajectories coming from one sector to get assigned to that sector. And then each trajectory or days are not split between different sectors. So that sort of could distinguish the country, try to distinguish the air mass history from different sectors. And I also have a few sensitive tests, and then the result on the final contribution is not sensitive to the threshold or a little bit wider or narrow of each sector. Thank you.
Thank you. I think at some point we should try comparing to the model, because we can actually shut it off. We can shut off the oil sands and then see what happens. It'd be interesting to see if we get the same fractions that you're getting.
That sounds great. Yes.
Yes, let's do that. Okay, so I think we should go on to the next speaker now, just in the interest of time. Thanks very much. Okay, so Jinyang Hao and modeling trace elements over Athabasca oil sands region in Alberta, Canada, using WRF-Chem. So if you could share your screen, please. And don't forget to turn your mic on too.
Yeah.
There we go. Okay.
Okay, could you say it?
It says double click to enter full screen mode. Try that. We don't see your screen yet. Oh, there we go. Now we do. Okay, we're good.
You can. Okay.
No, go ahead.
Okay, thanks for coming. My name is Jinliang Hao. I'm a PhD student in York University. I'm going to present my work on modeling trace elements over Athabasca oil sands region in Alberta, Canada, using WRF-Chem. So, okay, first background. The particulate matters are inorganic and organic chemicals, including major and trace elements. These trace elements could cause adverse the effects on humans, for example, the respiratory system, nervous system, and the cardiovascular system. They come from both natural and anthropogenic emission. They distribute in both fine mode and coarse mode. The fine mode means particle diameter smaller than 2.5 micrometer. The coarse mode means particle with diameter larger than 2.5 micrometer. The Athabasca oil sands region is one of the largest oil sands bitumen reserves in the world. And bitumen is a form of heavy crude oil. It is made up of particulate materials. So in bitumen extraction and upgrading byproduct, there will be some trace elements emission. And for trace elements, there have been some observations all over the world, but quite few numerical simulations. Until now, there isn't any numerical modeling simulation in Athabasca oil sands regions for trace elements. So with my modeling simulation by WRF-Chem, we can learn the impact of large emissions on the local environment, the connection between weather and pollution to local, the seasonal variation of dry and wet deposition. The model simulation is also a compensation for the discrete observation located in the large emission regions. So the model setup, the WRF-Chem version 4.1 or 4.2.1 is used in my study. The simulation is in January and July 2016. The two nested domains are shown in the right figure. The red box is just outside domain, covering the Alberta, and the resolution is 9 kilometers. The white box is the inside domain, covering the Athabasca oil sands region, and the resolution is 3 kilometers. And 8 trace elements are chosen in my study. They are aluminum, calcium, iron, potassium, magnesium, silicon, titanium, and zinc. because they are high emission in the just among all trace elements as shown in this figure. The upper figure is the total emission in fine mode, and the lower one is in coarse mode. So the red arrows indicate the 8 trace elements, and you can see there are 4 elements ignored. This is because first the sulfur is just a major element, and the other 3 species are unavailable in the concentration observation database for coarse mode. And these 8 elements just account for 91% of the total emission from all trace elements in fine mode, and they contribute 95% of the emission in coarse mode. Silicon has the highest emission, and followed by the calcium, aluminum, iron, potassium, titanium, magnesium, and zinc. However, these trace elements are unavailable in the Wolfram, so I have to add these trace elements with 4 size bins into MOSAC. The MOSAC is the model for simulating aerosol interactions and chemistry. It is just an aerosol scheme in Wolfram, and it was assumed there isn't any chemical reaction for these trace elements, just due to the limited knowledge on chemistry. And the main processes for these elements are shown in this figure. First, the trace element will be emitted from the surface, and you are in the air phase and undergo the transport. When these trace elements get into the cloud, a part of the air phase will become aqueous phase. If the cloud droplet evaporate, the aqueous phase will come back to air phase. And if there are some rain droplets inside the cloud, the element in the aqueous phase will be removed by the in-cloud wet scattering. And when the rain droplet falls from the cloud to the surface, the elements in the air phase will be removed by below cloud wet scattering. And the summation of the 2 wet scattering processes will be the wet deposition. And also the element in the air phase will also removed by dry deposition. The input data, the meteorological input data is from NCEP, FNL analysis data. The chemical data is CMOS. The biogenic emission data comes from Rachel. The biogenic emission data from Morgan. The trace element point and area emission is provided by the Environment Climate Change Canada. The result. First, I will just show the meteorological conditions. The upper 2 figures show the monthly average temperature and the wind speed. And our lower 2 figures shows the accumulative precipitation. And the red circle just shows a specific ocean region. So we can see in January, the temperature is around -14 Celsius degree, and the wind speed is around 2 meters per second. And in July, the temperature is around 16 Celsius degree, and the wind speed is around 1.5 meters per second. The precipitation in January is around 30 millimeter, and it is 80 millimeter in July. So this figure shows the monthly average concentration with unit of nanogram per cubic meter in all 3 sites. So we can see the black bar just indicates the observation, and the red bar is the model output. So in January, most of the model output is higher, around 2 times higher than the observation. And in July, however, the model output is close to the observation, or even lower, around half of the observation. In my research, the emission rate for each element in the 2 months are the same. So I think it may not be reasonable. In the later work, I need to modify this emission rate. And these 2 figures show the aluminum composition with unit of nanogram per cubic meter in vertical cross section. The left figure is in January and the right one is in July. So we can see in January, the aluminum just moves up to 2,000 meters just because of the weak vertical mixing and low pressure, low temperature in January. In July, however, it moves up to 5,000 meters because of the strong vertical mixing and high temperature. This figure shows the monthly average dry deposition flux with unit of nanogram per square meter per second in January. So we can see all trace elements concentrated around the asbestos ocean region, and they just spread in direction of north-south. Silicon has the highest dry deposition flux, followed by the calcium, aluminum, iron, potassium, titanium, magnesium, and zinc. This figure shows the dry deposition flux in July. Also, they just concentrated around the specific region, but they were spread in direction of both north-south and west-east. I think it is caused by the different wind directions in July. And silicon has the highest dry deposition flux than the order of magnitude for these 8 elements, just the same as just in January. This figure shows the cumulative dry and wet deposition fluxes with unit of microgram per square meter in all 3 sites. And we can see the black bar is the dry deposition flux, the red bar is the wet deposition. So no matter it is in January or July, the dry and wet deposition they are in the same magnitude, but the dry deposition flux is always larger than the wet one. And in July, the dry deposition flux is similar to that in January, but the wet deposition were increased because of more precipitations in July. Conclusions: the simulated concentration are much higher than observed concentration in January, but it is close to or even smaller than observations in January. The trace element dispersed to a higher altitude with stronger vertical mixing in January. Also, the emission rate for winter and summer may need modification in the later work. Both dry and wet deposition fluxes are both crucial for the elements removal. And the dry deposition is always larger than the wet deposition. The wet deposition will increase with more precipitations in July. And lastly, a longer simulation will be needed to validate my output or my conclusion. Thanks for your listening. Any question?
Okay, thank you. So are there any questions for G-MACH?
Okay.
I have a question. Your concentrations were biased high in winter. So how do you think that might impact your deposition results for winter? Like how much do you think you might have to scale those, or did you do some scaling on your last graph with the deposition where you're comparing the wet and dry deposition?
Oh, this one?
Yeah, did you scale that at all to account for that difference in concentration?
Oh yeah, from this concentration we can say, here the concentration in January is much higher than just in summer in July. But however, they are just dry deposition and dry deposition is just similar in both the winter and summer. So I think the concentration, although the concentration are different between the 2 seasons, but the dry deposition is similar.
Interesting. Okay, thank you.
Yeah, maybe just caused by different meteorological conditions in the 2 seasons.
Are there other questions for G-MACH? Okay, I had a quick one. As you know, with regards to a couple things, thoughts with regards to the emissions. What are you doing for particle size distribution for the emissions and in WRF Chem? Which methodology are you using for the particle sizes?
Oh, okay. I just go back to which one? Oh, here. Yeah, the emission. So emission for the elements provided is in 2 modes, fine mode and coarse mode. Okay. And in MOSAC, it will be 4 side spins. The summation of the first 3 side spins will be the fine mode.
Okay, so it's
last one is the coarse mode.
Okay.
So I need to just partition the emission in the fine mode into 3 side spins.
Okay, yeah, some of what's going on may be due to the relatively coarse resolution of the size bins. We're seeing some indication that the size distribution that you're assuming in the emissions is quite important. I'm not sure you'd be able to capture that in 4 bins. The other thing that I was thinking is that, you did mention the chemistry issue, and so you're not running inorganic heterogeneous chemistry within this setup?
Yeah, I just turn off all chemistry. Just in the air and in the cloud.
Okay,
yeah,
that's another one that can make a very large impact. When you'll see some of that in Stefan's talk coming up. Okay. Mark, where are we for time? Because you're the one doing the timing.
Yeah, no, we got a little time for more questions.
Okay. Any other questions for G-MACH?
Can I ask about the observations? Are those daily? Do you know what the frequency?
Oh,
measurements are?
there are three sides. For the first one, the third one, it should be around 3 days. For 3
Okay.
days, there will be observation. For this side, it should be around 3 to 6 days.
So those comparisons you're showing are for the entire model period, right?
Yeah.
Okay.
Yeah, I also have to do a monthly average. Just daily is not enough.
Oh, sorry, monthly, yeah, I see.
Yeah.
Makes sense. Okay.
Okay. I'm looking at the time right now. This is the start of our, I believe, this the start of our 10-minute health break. The next talk is 20 minutes after the hour. That'll be Colin Lee. We can, if people have further questions for any of the three speakers that we've already presented, feel free to ask them. In the meantime, next talk will be 20 minutes after the hour, just so you know. So, open the floor if anyone has questions about any of the three talks we've seen so far. I guess, I can follow up with a question for Jing Wang, maybe. Just
Yeah. Of course.
I'm interested in the, like this is no chemistry, and we've seen sometimes that chemistry has a big impact. A couple of things, like the base cations for the calcium, the potassium, the magnesium, and sodium. I guess we didn't have sodium in those. That does seem to have a substantial impact. The other one that's worth considering, what do you happen to know offhand what particle deposition algorithm you're using? This because it's dependent on size as well, and so I was wondering what you might be using for that.
Could you repeat, what do you want to know?
Oh, the methodology used to calculate deposition velocity of the particles as a function of size.
Yeah, okay. In the Wolfram, just consider all aerosols in one size bin and just calculate the average diameter for all aerosols in one size bin, and use this average diameter to calculate the dry deposition velocity.
Oh, understood. There's been some recent work by Emerson. There's a paper, Emerson et al., I think it's 2020, and I think there's been a more recent one than that too, where the way in which the size affects the deposition. There's been a lot of recent measurements where the algorithms have changed. And that's another one that the particle deposition seems to be quite sensitive to.
Yes.
So there may be more than one algorithm available within WRF-Chem. And if so, you might want to try toggling it to see how it affects the more recent, that is, if you use one of the more recent ones versus one of the earlier ones. You could
Yeah, a good idea. Maybe I try another deposition scheme to just check what's just the difference.
Yeah, it seems, from what we've seen, it seems to be quite substantial. The Emerson correction on Zhang scheme seems to be make quite a big difference.
Yeah, I had checked two deposition schemes in Wolfram. They both just trace just aerosols in one size bin and calculate just use one average the diameter to calculate. I have checked two schemes. Mm-hmm. Maybe I can check maybe the third one.
The other one is on the emission side. The part, I was wondering what sources of emissions data, but usually there's a seasonal correction as well in terms of fugitive dust and that sort of stuff. So you might want to check to see what you're doing with that. I mean, the assumption is that if the ground's frozen, you're not going to have quite as much dust being kicked up. So there may be some things happening there too.
Yeah,
it's very interesting work. It's sort of interesting to compare what you're doing with what we've seen.
Yeah,
what could be causing that, kind of thing. So,
yeah.
We can talk further in the future if you want to.
Yeah.
Okay. Just keeping an eye on the clock here. We still have about 6 minutes to go. So we're just going to wait if anybody has a question, and for the first speaker too, if you want them, please feel free. In the meantime, we're just waiting out the rest of the health break until 20 minutes after the hour. mute your microphone. Okay, there we go. And the
Sorry,
next,
I don't know if you saw my mouse floundering around. I was trying to figure out how to unmute and put my camera on.
it's all right. If you can back up to the first slide, and then we'll.
There we go. Okay.
Okay, so go ahead, Colin.
Hi, my name is Colin Lee. I am a physical scientist at Environment and Climate Change Canada. I've been working with Paul McCarr on this GEM-MACH oil sands work. And so today I'm going to talk about a little bit of the work I've been doing, particularly with hydrogen sulfide in the oil sands. So this map shows all of the oil sands operations that we've been talking about. And then right smack dab in the middle of there is a small First Nations community called Fort McKay. And the people who live there have obviously noticed that they are very oftentimes downwind from oil sands operations. And so the government of Alberta has actually put into place an odor event reporting system. So people who live there can go outside and say, oh, it stinks. And they can actually report that data. So there's quantitative data about the observed ambient air quality. Now, also in this region, at that same dot, the Oil Sands Monitoring Project has been running a monitoring site called ALLOCATION with high time resolution air quality and meteorological data. And then not shown on the map is the WBEA monitoring sites that Paul has talked about. And they're sort of scattered all around the region. And I should also acknowledge the financial support of the Oil Sands Monitoring Project at this program at this point. Okay, so the question that we're trying to answer is what is causing these odor events? And so the first question is then, what can the observations tell us? And so we have all of this nice data from ALLOCATION as well as that WBEA data. And then the next question is, can we use GEM-MACH to study these odor events? Because even though there's pretty good monitoring there, it's still not perfect. And so can we bring to bear all of the technical expertise we have in this model? And so that presents two sort of sub-questions, which is, do we track the species that are correlated with the events, and how well do we track them? And how confident are we in the emissions that we're using for those things? And so to answer the first question, at the top, there are some time series plots here of various VOCs and sulfur species. And the dots are color coded for time of day. And so the purple dots are the middle of the night, and the yellow dots are the middle of the day, and the green and orange ones are morning and evening. And then overlaid on top of that, I have the odor events as these gray bars. And so you can see that some of these species do seem to get higher when there are odor events reported. But other ones don't at all. And then also there's a lot of times when there are elevated concentrations that are not reported at all. And there's various reasons for those. I don't really have time to get into all that today. So another thing we did was a statistical analysis. So these are sort of bar charts overlaid with vertical histograms. And so the question is, can we see a statistical difference in the species between the normal background conditions? And yes, there was an odor event report. And so it turns out that hydrogen sulfide, H2S, is one of the best separated species. There were also a couple of VOCs, but the difference between H2S and those VOCs is that we don't have any representation at all of, or we didn't have any representation of all of H2S in GEM-MACH prior to this work. And in fact, it's not common at all to include H2S in terrestrial models. But we found that it was a pretty good indicator and not included, so we added it. And so to do that, we added a pretty simple oxidation to SO2 chemistry mechanism. And we also needed to find some emissions. And it turns out we actually have two sources for that emissions data. So one is the National Pollutant Release Inventory, or NPRI, and that is industry reporting to the government of Canada. And the other one is the Alberta Environment and Parks, and that's industry reporting to the government of Alberta. And the main difference between these two inventories is that AEP has more detailed spatial information. So NPRI reports at the facility level, so that would be, most of these would be all sort of one facility, but in AEP, these shapes each get their own emissions. And so I've overlaid on this map of where the emissions are coming from in the AEP inventory, the GEM-MACH 2.5 kilometer model grid in these blue lines here. And so you can see that if NPRI, if we're just spreading them out over all of this, we're going to get a very different answer for the shape of the plume if we were to concentrate them based on how AEP says we should. Apart from that, the NPRI and AEP inventories report very, very similar amounts of H2S being emitted in total. The other thing that's worth mentioning here is that the tailings ponds emissions in particular are a big source of uncertainty, because this pond is actually quite heterogeneous in real life. And also the time of year is going to change heavily how much is being emitted from there. But we're basing these reports to the emissions inventories on usually once a year they throw a float out to one spot in the pond for a few days. And so you can see how that would lead to a large source of uncertainty. So we're going to test how well GEM-MACH does using these two different emissions inventories for simulating H2S. And so at least I go to all these talks for pretty pictures. And so here's a pretty picture of how GEM-MACH simulates hydrogen sulfide. So you can see the oil sands operations in these blobs here. And these are the H2S plumes in a sort of roughly logarithmic color scale heading downwind. But the real question is, does this have any sort of bearing on reality? And so we have to evaluate the model. And I mentioned these WBEA or WBEA monitors. And so there's 8 of them that include H2S for our simulation period. And the other thing to note is that there has been some concern that the WBEA monitors suffer from interference from other reduced sulfur species. So different reduced sulfur species can get converted on intake to the monitor, and then they show up as H2S in the results. Now, fortunately, we have a WBEA monitor that's fairly closely located to the OSCE-UDEN monitor, and we have reason to believe that the OSCE-UDEN monitor shouldn't be suffering as much from these kinds of interference effects. And so we can use that to help quantify. And so the red here is the OSCE-UDEN monitor, whoops. And the sort of turquoise line here is the WBEA monitor that's located fairly close by. And you can see there's a bit of an offset, especially when the concentrations are fairly low. And then if we do a scatter plot and a regression, we get something around 0.2 ppb of background interference. So that gives us some idea of how much interference there is. And that's worth keeping in mind when we look at the future comparison plots. So if we compare the model to the observations at some sites that are very near oil sands operations, the blue dotted lines are the observations here. The green line is the model values using the NPRI emissions, and the red line is the model values using the AEP emissions. And so you can see that in general, we're sort of underestimating at OSCE-UDEN. We're doing okay at Mannix. Now this one is actually very, very close to the operations. And this one is sort of maybe 20 kilometers from the nearest operations. And the other thing to take home from this is that AEP increases what we see at the monitoring locations. Even though we're not increasing the total amount of emissions, changing the distribution does change the shape of the plume, which is kind of what we'd expect. If we look at these sites that are a little further away, then we see that, first of all, our change in the distribution doesn't make much of a difference. So again, the red one's the AEP and the green one is NPRI, and they're quite similar. And then second of all, we're also showing low compared to these monitors. Now, a lot of these measurements are sort of below that interference level that we're expecting, but a lot of them are above there. We're not even seeing those in the model at all. It's also worth noting that although these are far from the surface mining operations, these are actually fairly close to the in situ mining operations. And we don't have any emissions for that in the version of the model that we're doing right now. So that's something that we may need to include in future. So some of the possible causes of our model being overall bias low are that maybe we're doing a good job of the emissions and the chemistry, but our meteorology is not matched up. And you saw in Yuan's talk, some of the back trajectories can get very, some of the air trajectories there can get very complicated. So that's one possibility. But another possibility is that we just don't have enough H2S being emitted in the model. And another possibility is that our spatial resolution at 2.5 kilometers is not enough to capture the actual shape of the plumes. And so to check that first and that last one, if we kind of watch this plume, the red dot in the middle there is the OSCE-UDEN station. And you can see that it's not that the plume has high concentrations and they're just missing OSCE-UDEN. It's that the high concentrations are going over OSCE-UDEN and they're just not high enough. And then that last question about, whoops, too far. About the horizontal resolution not being enough. If that were true, we would expect that the model plumes would be much wider than the observed plumes, and that's not something we're seeing. So we don't think that's probably the case. And so then the question is, what happens? So it looks like this is probably about missing emissions, and one possible source of those missing emissions is the tailings ponds. I mentioned that we were. There are large sources of uncertainty there, and some colleagues did a study right on the shore of one of the tailings ponds, and they indicated that for that pond in particular, the value reported to NPRI was maybe around five times too low. And so we just, as a broad strokes first sensitivity study, jacked up all of the tailings ponds emissions by 5 times, which is not reasonable. We do not expect all of the ponds to match that one pond, but it's a good sort of first step. And we can see that again, the blue is the observations, the green is the old model, and the red is the new model with the 5 times pond emissions. And you can see, obviously, that does increase the H2S concentrations at Oskewton. But now we've totally surpassed the monitor at Mannix. Now, as I mentioned, Mannix is right in the oil sands operations. And one possibility is that in reality, Mannix is not downwind of these sources, but in the model, because it's in the same grid cell, it's getting those concentrations. So that's one possible explanation for that. And Mannix is one of the outliers, actually. Almost all of the monitors had this kind of situation where the 5 times pond emissions did a better job. If we look at the in situ ones, we do start to see some of those spike levels come up. So that's a little promising. But again, these are not near the operations where we increase the emissions. And we know that we're not including the emissions that should be occurring near here. And so the next step is to use some air trajectories and parcel analysis to sort of back out where we think high concentrations are coming from and do a quantitative study. So on this map here, the purple is where we think the emissions might be coming from, and the green is where we think they're probably not. We can do this for each of the different stations, and we're finding some agreement between them. So we're going to use that to sort of back out some better emissions estimates than simply increasing all of the tailings ponds by 5 times, because that's not very reasonable. And so just to summarize, we have added a simple H2S system to GEM-MACH, and overall it's more or less consistent with what we're seeing in the observations. But it is too low. And so this suggests impossible missing sources in the emissions inventories. And increasing the tailings ponds emissions by 5 times actually improved things at almost all of the monitor locations, except for 2 of them where it overshot the monitors. And so we're going to go hunting now for some more missing sources and tune that up. And I would just like to once again acknowledge the financial support of the Oil Sands Monitoring Program. And thank you for your attention.
Great, thank you very much, Colin. Mark, do we have
Looks
time
like
for
a couple minutes for questions.
Okay, questions for Colin?
I could ask, that was a really interesting talk. The in situ, the WBEA measurements, they seem to show that there's sort of always H2S around it to some degree. Is that like, do you think that's instrument you were saying with the, sorry, I forgot the word, but the interference?
Yeah, I think, I mean, if you remember on that scatter plot, the level's around 0.2 ppb. And so like these distant monitors, they're sort of at that level a lot of the time. They never kind of go below there except for here. So I think there's a possibility, but these are also near in situ mining. And I unfortunately don't know very much about in situ mining. I'm gonna have to learn a little bit about it. So there's a possibility that that's a source of H2S and other reduced sulfur species. So yeah, it's a good question, and it's one that I have to dig into a little bit more to answer.
At the same time, Colin, I assume though that the spikes above 0.2 are likely to be real, right? So,
I think that's probably true. Yeah.
Mm-hmm. we could probably go to the speaker then.
Okay.
Time.
Right, let's just keep it moving. So our next speaker is Stefan Miller, who will be talking about updating the inorganic heterogeneous chemistry solver in GEM-MACH. And notice this is the chemistry between the particles that might be of interest to Jin Liang as well. Just see what sort of stuff we've been up to with that. Go ahead.
Can you hear me and see my screen?
Yes, we can.
Okay.
You're on.
Okay, so I'm going to talk today about an update to the vectorized inorganic chemistry solver that's being used in GEM-MACH for the second annual run. And so just as a brief introduction, up to 50% of the dry fine particulate matter is inorganic by mass, and it's primarily composed of sulfate, bisulfate, nitrate, ammonium, sodium, and chloride. But we also have coarse mode particles, cations, that are also important. And so previously, Het V was written by Paul back in 2003, and that did not include the base cations or chloride or sodium. And so this new version includes those new species, and it now partitions not only between the nitrate and ammonium, but it also does chloride and hydrochloric acid gas. And so we want to use Het V2 to investigate how these base cations deposited to foiled surfaces are going to affect the pH, which may impact the deposition of SO2, which was recently shown in a good paper by Catherine Hayden. Okay, so just a solution procedure. I'm just going to go through it briefly. So the solution is broken up into 4 branches, and then each of these branches has subspaces that represent a solution. And so the first step is to determine what branch we enter, and that's determined based on the input species that we have. And so these are total gas plus aerosol species, so they include the liquid phase as well as the solid and the gas phase if they were present. And then each branch has 3 to 5 metastable states. And so metastable here implies that there's always water present and that we're going down the efflorescence curve and there's no solids precipitating out. And this is probably a reasonable assumption near the surface, but might not be too applicable higher up in the atmosphere. And so just briefly then to go through the branch that's like the newest, most important branch, I guess, to be added here is the one with the crustal species, including the chloride speciation. And so based on this, there's 5 different subroutines that will determine the species that result. And we determine whether what we enter here based on these sulfate ratios. And you'll notice that the chloride and the nitrate are not included in these since they they're not included in the ratios. So I'm going to just talk briefly about the Calico 7, which is the sulfate pour, dust and sodium pour routine. So Calico 7, M8, and P13 are the most complicated routines in the package. And so it starts off by calculating equilibrium reactions and getting the equilibrium constants. And so there's a system of equations that's solved, and there's n equations and n unknowns. And we have our equilibrium reactions and we have mass balance, and we use these together here to get an estimation of the HNO3 gas and the particle phase NO3. And so once we get those, we can move on to the next step. So it's an iterative procedure where we're constantly trying to estimate all of the species in order to get a concentration that we can use to estimate chloride. So dry partitioning is applied. We assume that all of the species have delquest, and the dissociation reactions are used to partition the species. And so from this, we can then use electroneutrality to determine what we should expect for this delta C value. So it's a perturbation analysis that we're doing. And then from this, we end up with a quadratic equation, which looks complicated, but it's really quite a simple equation. But the issue with this is when the coefficients here, for example, B and C, become similar orders of magnitude, the quadratic can be evaluated incorrectly. And this quadratic equation appears several times in this routine, and it's iterated many times. So it could potentially be solving these quadratics thousands of times in a single subroutine. And so if there's an instability that occurs at one instance, it will carry through the entire routine. And so the next step after we've calculated our NH4 and NH3 speciation, we then calculate the hydrogen ion calculation, which is another quadratic equation. And then once we estimate that, we have all of the necessary concentrations to estimate the chloride concentration. And so the first step is to determine where the chloride, where this function changes sign. So we want to determine a root exists on a specific interval. And then once we have that selected interval, we subdivide it further using a bisection method until we converge within a set tolerance. And then after we've converged, we do our minor systems. And so this would be our HSO4 speciation, since we're in the sulfate poor case. And then we also have other considerations that are really important, especially at low relative humidity. The concentration in this, or the solution becomes very, very non-ideal and concentrated, and so you get a really high ionic strength. And when you have this high ionic strength, you have these activity coefficients that pop out. And these are a very computationally demanding task that has to be applied. And about half of the time is actually spent just calculating the activity coefficients. And so once we've calculated all of these quantities, we can use the concentration at equilibrium then to determine how the mass of the particle is going to change with time. And so that's the main goal of this, is to determine this. And so what did we do to Het V2 that's improved it? So the first thing is we've updated the routines to Fortran 90, which is important because it was originally in Fortran 77, had many go-to statements all over the place. They use include statements for declaration of variables. So we've removed all that. Het V2 also now will solve all cases simultaneously instead of having to be called for every individual set of initial conditions. And we've also replaced all of the quadratic equations with a Taylor expansion that's only used in times when the quadratic might be improperly evaluated. So this is just one example of the quadratic that's used. And there's a few different ones depending on the sign of the radical. Okay, so other things that we've improved. So some of the solutions also require a cubic equation to be solved. And so we'll apply bisection then if it's necessary. We've also improved or corrected the mass adjustment routine so that it actually includes calcium sulfate in the mass balance calculations. And we've updated L9 to include mass balance expectations that were not being properly applied. And so we were missing mass coming out of that routine, but we've added that back as the gas phase at the very end of the routine after it's converged. Okay, so now for the actual like some results of how this has affected the measurements. And so I just want to point out two main areas here. So this is a case where we're at really low relative humidity, but a relatively cool temperature. It's probably a little bit lower relative humidity than what's normally seen in the atmosphere, but this is probably like one of the lower cases, I guess. And so we find out that when we use CMAC, we end up with a negative bisulfate concentration, and a lot of instability shows up at high total sulfate. So this just to some background. So all the species here are held constant except for the total sulfate, which is allowed to vary over a range. And so the top graph here is the original isopropia, which is being used now in CMAC. So this is actually being used and they're getting these results. I didn't see any corrections in their code that dealt with these negative numbers. So I don't know what they're doing with that. But when we use the corrected root, those negatives disappear and our solution is now a nice smooth function. Similarly for L9, we see a similar effect happening, and it's maybe a bit less pronounced than in I6. So in general, the effect of adding these new numerical methods to solve the roots has improved the solution space and removed a lot of the instabilities and negative concentrations. And these are just two examples, and these instabilities do occur at more reasonable temperatures and relative humidities as well, but they're just not as pronounced as here. Okay, in terms of computational speed, so one of the issues too that we want is we don't want to rewrite this, rewrite isopropia and then have it come out slower. So one of the issues was we want to make sure that it's faster. And so I spent a lot of time trying to speed it up. And so most of the routines now are faster than the original isopropia, except for H6, M8, and P13 in this case. So just for some background, this is the average of 10 individual executions for 100 grid points. So CMAC would do grid point by like single case and then call another case, whereas Het V would do them all at once. And so we can then look at higher number of cases, so 1,000, then we're only slower in 07. So in general, Het V2 is quite a bit faster in most subroutines than the original isoropia, while giving better results in some cases.
A quick comment there. I think that in your bullet point, shouldn't that be Het V2 is faster than isoropia 2, the blue columns?
Sorry, yes.
Okay, no, that's fine.
Thank you.
Just wanted to clarify that for the audience. So
Yeah,
all
so-
those negatives mean that it's faster than the original.
Exactly, sorry about that.
No
And
problem.
then this would be the only one that's slower. And so we can do the same thing now, but now we optimize the code. So use an O2 optimization flag, which will force vectorization. And in this case, then we've increased the computational speed of Het V2 even more. And so Het V2 is now even faster than isoropia without using optimization. And then there was an issue too that GEOS-CHEM, there's another implementation of isoropia in GEOS-CHEM, and they tried to optimize the isoropia code, and they found that the results that they got after optimizing were not the same as what they got before optimizing, which is probably related to the go-to statements and the fact that declarations are not are done in an include statement. And so they don't actually optimize. So it's not actually recommended to optimize the original isoropia code, but our results are the same regardless of whether or not we optimize. Okay, and then just for some example impact on the GEM-MACH simulations. So in this instance, it's one day, June 14th, 2018. I just looked at one day. And the plots here demonstrate the difference between the new Het V and the original two cases without the base cations or without the chloride and the calcium. And so we find that in most instances on this day, Het V2 indicates that there's lower amount of HNO3 than what was present in the original Het V routines. So that implies that adding in the addition of the base cations, the calcium and the chloride, has led to an overall decrease in the amount of HNO3. And there's also a corresponding increase in the particulate nitrate as well, which I don't show here. Okay, so then just to conclude, we've developed a new inorganic heterogeneous chemistry solver based on isoropia 2.1 algorithms. And the new solver has improved the accuracy from the updated numerical methods to solve the quadratic and cubic equations. The new solver also runs 65% faster for some of the subroutines, and then Het V2 can also be optimized, which will give an even faster execution time. And then initial tests now suggest that new solver is having a positive impact on the performance of HNO3 prediction, and the known positive bias that we see in the GEM-MACH oil sands Athabasca region is reduced. And so next steps will be to extend this to the non-metastable state subroutines, to further optimize the code, to look at pH on the foliage surface, and then perhaps add in other species such as bromide or even organic acid, which have been shown to potentially be important as well. And I just want to acknowledge the financial support of the oil sands monitoring program. And does anybody have any questions? And thank you for your attention.
Thanks very much, Stefan. Mark, are we okay for questions?
Yeah,
Okay.
a couple minutes.
Okay, questions, please.
I don't know how to do a hands up. It's Kenjiro.
I can do.
Hi.
Go ahead.
Yeah, it's a great work. I'm really impressed. I have two implementation side of the question. Do you account for the size distribution for the aerosols for the computation of Het V thermodynamics equation? Is it just the one being assumed for the thermodynamics?
Yes, so it's using the total amount. So it would be added up all the bin sizes, and then after it partitions, then it would rebin based on what the mass changes.
Okay, but in reality, there could be some difference in how ammonia and nitrate could be distributed.
Yep.
And do you think it could be a source of the error somehow?
Possibly, but we haven't really looked into that. So that should be something to look into, I think.
A comment there, Kenjiro. Yeah, the kind of thing that can happen is, if you use these codes to calculate the local equilibrium as opposed to bulk, you can see things like mass transfer between the fine and the coarse mode. A nitrate, for example, blowing off the ammonium nitrate in the fine mode and going to the calcium nitrate in the coarse mode. The issue though is the algorithms tend to be one of the most computationally intensive of the whole air quality model.
Yeah.
And so that's why they tend to be used in bulk. Now, if we can get this sucker to run faster, we could at least try splitting it up and do a local calculation for both ends of the size spectrum. What we try to do right now in the model is there's a redistribution of mass that's based on the Fuchs-Hutchinson gamma factors to at least say, okay, where we think the mass is going to go, but it's not based on a local equilibrium. But that's the sticking point has always been the time, the CPU time, and we're trying to see if we can get it down fast enough to try to include some of that sort of thing.
Okay, I have another question. For the base cations, do you assume that all of the base cations are not refractory, like in dust? Some of the calcium and magnesium are not really mobile, I think. I mean, like calcium oxide and.
Yeah. So there is a salt that comes out, like calcium sulfate, which is assumed to be completely insoluble and just kind of sits there. And doesn't really impact the system except for the mass balance. So yeah, I guess we should really think about adding in the precipitating salts as well.
I think on the emissions side of it, Kenjiro, we are making the assumption that the base cations that we're including in emissions are ones that are potentially soluble, and that's part of the data that's been collected for the emissions database themselves. So there may be an insoluble calcium that's not part of this, but it's assumed that it's at least potentially soluble. And then there's what the algorithm does to it, as Stefan said. And if it goes into calcium sulfate, it seems that it's not coming out again. But we could include more of the salts. We're, as you said, this is part of the system. It's the metastable state part.
Okay.
Yeah, we've completely ignored the non-metastable state because it's not typically used in any of the global models.
I think Mark is.
Yeah, I'm sorry. We should. Why don't we continue the discussion after the last talk?
Okay. Thank you very much.
And for our last speaker, I believe Chris McClendon is standing in for Deborah Griffin, who couldn't make it today. Chris, are you there?
Yes,
lovely.
Absolutely.
Okay, and please share your screen. Let's see if we can get your.
Okay.
Okay, and then slideshow.
Yeah.
Okay, we're still waiting for it to go into slideshow.
Yeah. Oops, sorry. Yeah, so this is work by Deborah Griffin, who unfortunately couldn't make it, but she really is taking it up from one of our co-op students, Sarah Moser. So
Chris, quick point. We're still seeing it in not in slideshow mode.
Sorry. Okay, there we go.
There, thank you. Okay, go ahead. Thank you.
Yeah, so we've heard lots about the oil sands already. So here's, that's the mailman. Right, so lots of emissions of different pollutants, but I'm going to focus on two types of sources, a mine fleet and some stacks. So right, the mine fleet refers to these really big trucks, these sort of iconic dump trucks that one sees, and they're a source of NOx, and as well as some of these stacks, these upgrading stacks. NOx, we think we have a pretty good handle on their emissions, and so what we're going to try to do is leverage those, combine them with aircraft observations of other species where maybe the emissions aren't so well known, and try to combine those to get emissions from other species. So here's an example of one flight where the plane flew around one facility several times and sort of was able to build up these walls of concentrations, and that's really sort of the basis for a lot of the aircraft flights. We're gonna take satellite observations where the satellite is used to observe NOx emissions and combine that with observations of other pollutants, NOx and other pollutants from aircraft. And so we're going to take the NOx emissions and then derive from the aircraft ratios of species that seem to be well correlated with NOx, and use that combination to estimate annual emissions. And so some of the species that we found to be well correlated with NOx are black carbon SO2, carbon monoxide, HCN, HONO, methane to some degree, and CO2. And for most of these, maybe with the exception of methane, these are sort of co-emitted as byproducts of combustion with NOx. So that's the main reason why they're correlated. As far as the aircraft measurements go, we derive ratios using two different methods. We're really going to focus on this correlation analysis, but there is sort of a complementary method, which I won't go into at all, which tends to provide very similar answers. So one source of emissions we're going to use are from the TROPOMI satellite. TROPOMI is a European satellite, stands for Tropospheric Monitoring Instrument, and it measures NO2. And from that, we have developed methods to derive emissions of NOx, which, again, I really don't have time to go into, but here's sort of a flavor for the process, where we use these sort of customized plume functions to relate the satellite observations back to emissions. And so the fitting procedures are done, and we can even, to some extent, derive spatial information, right? So these polygons on the right represent boundaries of sort of facilities or locations that we expect NOx from which NOx to be emanating. And these are almost all oil sands operations, although not exclusively. And so from this, we can derive annual emissions of NOx. Using similar approaches, TROPOMI is actually sensitive enough to, pending the meteorology of the day, derive emissions from single overpasses. So it's quite nice in that way. So most of this analysis is really going to focus on the annual piece, but there's also potential to use and derive daily emissions for some of these compounds based on the daily NOx emissions. This can't always be done, and sometimes it's hard to disentangle two facilities that are adjacent, but nonetheless, on some days, this is certainly possible. Okay. Right. So, we have our NOx emissions, and we're going to use the aircraft measurements to derive these ratios. Now, here's one flight, and so I showed you that sort of box earlier, and if we sort of split that up into the four sides, these are the concentrations as a function of height. And so we can see many of these species are correlated with NOx. And one is black carbon, right, which we believe largely emanates from the trucks, so it'd be a little bit lower, more of a surface source. And another is SO2, which is really more linked to the stack emissions, which is why it's a little more elevated. And so, but really the spatial patterns are very similar. And indeed, we can use species like black carbon and SO2 to help disentangle ratios for different source types. So if we plot, for example, if we scatter plot now black carbon versus NOx, we see two different branches of emissions. One corresponding to low SO2, which is interpreted as corresponding to the mining fleet, where we don't really expect much SO2 to be coming from, and then the stack emissions, where we expect to see SO2, elevated SO2. And so we get two distinct ratios, although the stack emissions ratio is much smaller. And so not only can we start thinking about emissions from individual facilities, but actually trying to break it up between these two emission types. Right, so if we develop these scatter plots for several different compounds now, several of these ones that seem to be correlated with NOx, we get this sort of family of plots here. Black carbon, we saw more or less from the earlier slide. Some of them don't seem to have this distinct branching between the two sources, which could mean either only one of them is emitting, or they're emitting more or less in the same ratio. Methane is a bit more complex. There does seem to be some correlation with NOx, but for at least some of the points, but for others, and maybe even the highest methane values, there's no correlation at all. It seems to be unrelated to the NOx. So that maybe requires a little more study. Another species is CO2, which is really a whole other study. I'm not going to touch on it here, but it definitely has a correlation with NOx as well. Right, so I think that's all for this plot. So now if we go and, so this was for one particular flight. There were several such flights. And so if we sort of combine all of that to get emission ratios for the various facilities. So these are 4 different facilities that were targeted during the 2018 campaign. And so we can derive emission ratios. And in some cases in which there are reported emissions, we can take those reported emissions and derive effectively a reported emission ratio by ratioing those emissions. And so for the most part, I would say this correlation method, which I've been discussing, and this alternative method using aircraft observations, which I really haven't touched on, are fairly consistent. And as I was saying, in some cases, we can even start isolating the different emission types, right? The stack emissions in the fleet, and derive their own individual ratios. And here's I'm showing this for black carbon, where the reported values and for the fleet tend to agree much better than with the stack. So we're sort of still sorting this out. I mentioned this work had been started by my co-op student, and really Deborah's just sort of taken it up again recently. So a lot of this is sort of redoing or updating what our student had done. So there's not a lot of interpretation yet, but we have gotten to the point where we're actually estimating emissions for some of these compounds. And that's what I'm showing in this last result slide here. So sometimes they agree, and sometimes we see discrepancies. Here's an interesting one here for black carbon, where for this one facility, there seems to be more reported emissions than would be suggested from this combination of satellite and aircraft observations. Likewise with Hono, it's more the other way around. We see more emissions than, there's not really reported here, but there were some emissions assumed in the model that were maybe a little bit small. I think in the model, they were just assuming some fraction of NOx, 1% or something was present as Hono, or maybe it's 0.5%. And we would suggest maybe it's more like 1% or double that. So I think Paul alluded to an update from this work earlier, and I think that's the one he was talking about. Yeah, so I would just say early days, but I think this is actually a very interesting method, and can be quite useful for some species that are maybe a little more uncertain. Everything I've shown has been for annual emissions, but again, there is the opportunity, as these ratios appear very robust, to apply them for daily emissions derived from satellite. And I think I will just leave it there.
Great. Okay, thank you, Chris, and especially thank you for stepping in for Deborah to deliver the talk. Are there questions for Chris?
If I could start, thanks, Chris. That was really interesting. The SO2 NOx correlation really surprised me how strong that is. I thought there was more emissions from trucks and things like that. I wonder though, might that relate to like the fact that the aircraft can't fly close to the surface, and if these are being released from trucks, maybe it's not as hot. They're sort of hidden down there.
Yeah, good question. So I'm just going to go back to that because I haven't really seen that one in a while. So you mean right here?
Oh, you're not sharing your screen.
Oh, I'm sorry. I thought I was. Thought I switched back. Yeah. Okay. Yeah.
There we are.
So,
Yes. Yeah.
yeah. So
It just went dark.
Lost
shoot.
it. Right. And the
went dark.
slideshow.
Ah. Okay. Yeah. Right. Yeah. So certainly this course, these dark points here where black carbon is small, according to the scale, that's the stack ratio. I don't know what to make of this. This is maybe more where the fleet would be.
Yeah.
So I don't know if that's a real small, I mean, if it's a real ratio or it's just kind of noisy. But yeah, certainly we do see a strong correlation when black carbon is small.
Yeah.
That answered your question really, but
Yeah.
if it didn't, then I don't know the answer.
Yeah, maybe it's unknown without being able to measure close to the ground.
Mm-hmm.
Yeah, thanks.
Are there other questions for Chris?
I have one. It's Kenjiro again. Do you think Hono could be somehow influenced by heterogeneous reaction as well by, I don't know, some kind of aerosols co-emitted?
I think you're confusing me with a chemist.
Yeah, because NO2 can be part of the NO2 emitted from something could be converted to Hono in the atmosphere by the reaction on the aerosol surface. So I was wondering if there is some indication for that kind of reactions happening after the things have been emitted into the air.
You mean that's showing up in this analysis? You mean that
No, just asking. Maybe it's just this
Well,
linear
generally.
correlation means just both are co-emitted, but
Mhm.
but this heterogeneous reaction could be fairly rapid.
We do see some evidence for it in the aircraft observations, Kenjiro. There's talk with Jeremy Wenzel about it. We can see that the Hono predicted by the model, if you do not include a surface reaction, tends to be bias low.
Okay.
And it needs to have that in there. We also see evidence of an HNO4 formation in the wintertime near the surface. That's in the observations, in the aircraft observations, and you know, unless you look at the surface reaction, you know, perhaps on the snow, you probably won't get that one right in the wild either. So it is there. You know, I'm not sure how it would translate into the satellite.
Okay, because Hono could be relatively short-lived during the daytime by photolysis, and it's not really conservative, unlike CO and HCN, even within the pixel scale.
Yeah.
Okay, thanks.
I think unless there's other questions for Chris, then I think the session is done then. I want to thank all the speakers for doing a great job of keeping on time and also providing some very interesting information. It's well done all. Appreciate that. And I think, I don't know, Mark, did you have anything you wanted to add? Or?
Just a general thanks to everyone for all the talks for all the air quality sessions so far. And this is our final AQ session of the 4. Of course, lots of other interesting stuff through the conference. So, but yeah, no, thanks again.
And thanks to our volunteer for helping us too. That's appreciated.
Absolutely.
Okay. Okay, in that case, I think we can stop the recording and